Solving a second-order linear differential equation yields two undetermined integration constants. Those constants can be found if y and y prime are given at the initial point x, for example at 0. If all conditions are given at one point x, we have a so-called initial value problem. Conditions can also be specified at different boundary points. In that case, we have a so-called boundary value problem. Problems of the second type are usually harder. We'll encounter a few examples in this video. About initial value problems, IVP, versus boundary value problems, BVP. And we do that using an example. We have y double plus y equals 0, and we set y 0 to 0. And then we do 4 examples in one example by taking 4 different second conditions. In A, we will specify another condition at 0. We put y prime to 0 at y prime at 0 to 1. And we will do 3 boundary value problems by setting first a condition at pi over 2, then a condition at pi, and then other condition at pi. So let's do our the first part of the example first, because it's the same for all 4 of them. So we solve our differential equation. We set y of x equals e to the power rx. Use the characteristic equation r squared plus 1 equals 0. So r equals plus or minus I. So the general solution would be c1 times e to the power alpha times cosine beta x plus c2 times e to the power alpha x times sine of beta x. So the general solution will be c1 times cosine x plus c2 times sine x. Plug in this condition they have in common, y of 0 equals 0. That yields c1 times cosine of 0 equals 1 plus c2 times the sine of 0 equals 0. So c1 plus 0 equals 0, or c1 equals 0. So we are only left with c2 times the sine of x. Okay, so far so good. Now the different conditions come into play. First of all, we take this condition A about y prime at 0. Well, we have our y, c2 times sine of x. We differentiate, we get c2 times the cosine of x. So if we plug in x equals 0, we get y prime of 0 equals c2, and the condition tells us that it should be equal to 1. So our solution finally would be y of x equals sine x. Okay, no problem at all here if you have an initial value problem. For a boundary value problem, you have to be a bit more careful. First one, at b, at y equals pi over 2. So we plug in x equals pi over 2, we find c2, we set it to 1/2, so y of x should be 1/2 times the sine of x. In this case, no problem at all. However, in case C, we want to have y of pi equals 1. However, if you put in x equals pi into y of x, we get c2 times sine of pi equals 0. So y of pi will always be equal to 0 and never equal to 1. So we cannot satisfy our second condition, no matter what choice we make for c2. So in this case, our problem has no solutions. And then if we continue with the fourth one, y pi equals 0. Well, if we plug in x equals 0 in our solution, we get c2 times 0 equals 0. So that's always true. So in that case, c2 is not specified. Y of x equals c2 times the sine of x, where c is a free parameter. c2 can be any value in R. And a general remark, also numerically in general, initial value problems where you have all your values at 1 point are much easier than boundary value problems. However, in physics you often encounter boundary value problems because you have physical constraints on more than 1 point. So let us finally look at those cases B, C and D. Well, we see here the sine of x. So our y of x was c2 times the sine of x. Well, if you adjust your c2, you can basically adjust the amplitude over here at pi over 2. So if you need, for example, 1/2, you can adjust your c2 to get a smaller sine in order to get this correct value over here. That was for case B. Then for cases C and D, we wanted some condition at pi. But no matter what you do with your amplitude, you always end up at 0 if x equals pi. So that's why you can get either no solutions, because you specified something wrong at pi, or infinitely many solutions, because no matter what amplitude you chose, you always ended up at 0 over here. Now this is a general feature of boundary value problems. They can have one solution, or no solution at all, or infinitely many solutions.